Hi, Dr. Kuhn. Today we're going to talk to you about catalyzed dimethyl ether production from methanol. And it's Hector, Paige, Josh, and myself, Dominique. To introduce the topic a little bit, dimethyl ether is mostly used as an intermediate chemical. There's a lot of research going on right now to use it as an alternative fuel source. I actually think there's a plant in India that uses it on a large scale as an alternative fuel source. It's also used as an aerosol propellant. Things like shaving cream, other products, and an aerosol can. It's made from methanol with the aid of a catalyst, methanol and water. And the catalyst that we chose for this reaction was the gamma alumino catalyst chosen due to the low cost and high availability, which we'll talk about a little bit more later on. Some of the project objectives were to create a reactor that would produce dimethyl ether from methanol, decide the scale of the reactor, identify any side reactions, establish the mass and energy balances for this reaction, note any safety considerations, and also we conducted a parameter analysis in that lab, mostly on temperature, and also to try and figure out some of our other parameters that we may not know.
So for our desired reaction, we have dimethyl ether and water forming from methanol. And for our undesired reaction, we have dimethyl ether forming C2 and C5 olefins in water. However, this wasn't taken into consideration because it's negligible at ideal operating temperature. For our catalyst selection, we chose gamma alumina. This is due to it being inexpensive and being the most well-researched catalyst associated with our reaction choice. For our rate law, this was taken from a research paper. The linear Hinshelwood mechanism is actually pretty frequently associated with this reaction. However, our rate law is not based on that because this rate law was found to be more realistic in terms of representing the kinetics of our reaction. And for our reactor selection, we chose a packed bed reactor. They are most frequently used for the solid catalyzed gas reactions such as ours. And they also have the advantage of being continuous operation and having a high conversion per unit mass of catalyst.
In designing our PBR, we had to use a few engineering assumptions to make it simpler. One of them is to neglect the influence of water, which is a good assumption because industrial grade methanol is found to have 99.85% methanol in it, so that the water content in that is negligible. We assume steady state, adiabatic PBR. This is very important for our derivation of our energy balance. We have negligible shaft work. We have no drop in pressure, and this is due to our preliminary design and to make our numbers work out. There's no phase change. This is according to our book Fowler, which we use to help us derive the design equations. All the following assumptions are needed for the energy balance.
Okay, so one of the first things that needs to be done in order to design this packed bed reactor is the material balance. And also we'll need a kinetic data such as rate of reaction of methanol and stoichiometric information, which is shown right here. So the concentrations of methanol, dimethyl ether, and water are shown here as a function of conversion and the gas expansion factor. The gas expansion factor ends up being 0 because we have 2 moles of reactant going to 2 moles of products, which therefore will give a delta equal to 0. And delta times the mole fraction will give a 0 times the gas expansion factor will be a 0. Thus, the gas expansion factor will equal 0. Also, with this taken into account, the volumetric flow rate can be considered constant, even though we do have this gas phase reaction going on.
So for our energy balance on the PBR, these are the specific assumptions that we needed to actually solve that. First of all, adiabatic is needed to solve this. No phase change as stated before. And especially constant heat capacities need to be constant because if we used the variation of that equation that depends on temperature, this would be a lot more complicated for a preliminary design. All the reactants enter the reactor at the same temperature, and this is the general equation for the energy balance, which can be reduced down to just these two terms. Continuing on, this is the final equation that we derived from the energy balance, and we needed this term, which is calculated from above, and that is the heat of reaction for our dimethyl ether production.
Okay, so with the given rate law for the formation of dimethyl ether, we have some specific kinetic parameters such as the rate constant Ks and the absorption constants Km and Kw. These will be used in the rate of formation of dimethyl ether equation, and as you can see, there will be a function of temperature. So in designing this packed bed reactor, we'll be varying the temperature in order to find out the optimal conversion. And right here is the design equation, which is the change in conversion with respect to catalyst weight, which is equal to the rate of reaction of methanol. So the material balance was solved in MATLAB using OD45. It was used varying the temperature, and we found that the temperature was most optimal at 600 Kelvin. At 600 Kelvin, we found that the conversion was at 70%. And at 70%, we found that the catalyst weight will be 383 kilograms of catalyst. Now, knowing the catalyst density, we'll be able to find the volume of the packed bed reactor, which came out to be 0.55 cubic meters. Okay. So in this slide, we have a plot of the molecular rates exiting the packed bed reactor as a function of conversion. So with designing the packed bed reactor, the volumetric flow rate is considered constant, and using a basis of 483 tons of DME produced, we were able to derive a volumetric flow rate of B to be 21 cubic meters per hour, with an initial concentration of methanol being 1 kmol per cubic meter. Now, so at 600 Kelvin and 70% conversion, our exiting molecular rates of methanol, dimethyl ether, and water are 0.64, 0.73, and they are 0.73 kmol per hour respectively.
In conclusion, our project, we approached by using richer values by acquiring data for equilibrium constants, rate constants, and absorption constants. After that, we were able to use design equations in the material and energy balances to create our specific packed bed reactor design equation. From that, we were able to use MATLAB to simulate the packed bed reactor and the conversions we were able to get out of that. With our data, we're able to proceed to stage 2 in the future, which is a feasibility analysis economically of this project.
And here are the references.